Hey you guys, this is Unit 3 Notes number 2. We're going to be jumping into section 3.3, okay? Notice how the section numbers are a little bit off. It's just that this is a better sequence for you guys in terms of understanding it, okay? Go ahead and write down the FLT and press play whenever you're ready. Okay, given a function, you're going to be able to find the intervals where f is increasing or decreasing, and also where f has any local extremas. So in the last section, we were diving into specifically absolute extremas, okay? So remember, absolute extremas can occur at the endpoints or at a critical number, okay? A critical number is where the derivative is equal to 0. So a lot of that doesn't really change in this section here, okay? You're going to see how it carries over. So instead of absolute extremas now, we're just going to focus specifically on local extremas and what's happening before and after that, okay? Okay, here we go. Take a look at these two graphs, okay? Go ahead and draw these out separately. Give it some space. We talked about it in the previous lesson, but what we're going to do now is we are going to study, okay? We're going to study how the derivative is related to the original function, okay? What's the relationship between the two? So take a look right here with this parabola. We'll call it f of x equals x squared here, okay? Now, if you were to describe it, okay, from left to right, this function, this parabola initially decreases because it's going downwards. So it's decreasing, but then eventually it stops decreasing right about there. So I'm going to make a note that right there it was decreasing because it's going downwards. The y values are getting smaller, okay? And then right after 0, it starts to go upward or increase in y values. Okay? All right, so here's what I'm going to do now. Now what I'm going to do is I am going to study the derivatives at several points, okay? So take a look here. Remember, we talked about it in the last lesson. When you're drawing a tangent line, it's not necessarily just a line that intersects the curve once, but it is drawn specifically a certain way where it's always hugging outside of the curve, okay? So for instance, this right there is not a tangent line, even though it intersects once, okay? All tangent lines hug the curve on the outside of the curve, okay? So if I were to draw one here, you would have a tangent line like that, or a tangent line like that. And I'm just drawing it at specific places here, okay? Here I have a tangent line like this. So I'm drawing a bunch to see if there's a relationship here. All right? Okay, we're going to come back to that. So let's take a look at this cubic function right here. Okay? Or odd degree function, I should say. So notice how the graph starts to go upwards, increasing in y values. So it starts to increase. Then eventually it stops increasing and then it'll decrease. And then eventually it stops decreasing in y values and then it starts to increase again in y values. Okay, so increase just means it goes up, decrease means it goes down. Okay, so let me label that right now. So it starts to decrease at these purple intervals, and then it starts to increase at this. Wait, I got that wrong. I got that flipped. Whoops. Why didn't you guys correct me? Decrease. increase, increase. Okay, I'm going to go ahead and get rid of the highlights. And then what I'm going to do is I'm going to draw a bunch of tangent lines, just like that last one. So if I were to pick these points here, again, I'm just picking random points. And you could try to mimic what I'm doing here, but the tangent lines would look like this. Now, hugging outside of the curve gets weird because it kind of depends on the curvature of your graph. We call that concavity, but we'll get to that later. Concavity just studies the curvature of your graph. Okay? But here's what's important, all right? What we're going to do now is, remember, the slope of a tangent, right? The slope of a tangent is a specific value, okay? So if you take a look at this first one here, this tangent line right here is pointing downwards, meaning that the slope has a negative value, because the only way to make a line point downwards is if the slope is negative. So I'm going to write it for the first one here, okay? Just for the first one. The slope is negative. Okay? And you notice that the second one here is also negative because it's pointing downwards. And this slope here is also negative. Okay? Now this right here, the point at where it changes directions, the slope is 0. Okay, because it's horizontal. Now if you notice over here, the slopes of the tangent lines start to point upwards, implying that the slope is positive. Okay. So let's do the same thing here for the cubic function. Okay. Go ahead and label the signs of your slopes and then press play whenever you're ready, okay? All right, so you should get positive, 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 0, negative, negative, 0, positive, positive. And we could have drawn more tangent lines, but we're only going to draw enough to kind of see a pattern here, right? So remember, we're looking at the value of the slope. Okay, so this is basically your quote-unquote rule, okay? But you guys are going to explore and figure this one out. What do you guys notice about the function's direction and the sign of the derivative? Okay, I want you to pause and think about that, but I'll say the question again. What do you notice about the direction of your function and the sign of the derivative? Is there a relationship? Okay, press play whenever you're ready. So take a look. We notice that when the function is decreasing, the derivative is always negative. So let's see if that's true over here in the second graph. When the function is decreasing, the derivative is negative, okay? Now, here's what you guys don't want to say. Don't use vague words like it, okay? Especially in this section, okay? Or in this unit, actually. You need to be very specific about what's changing, okay? So, listen to my words very carefully. The function is decreasing the same time the derivative is negative. What you don't want to say is it's decreasing, so it's negative. Okay, you got to be very specific, especially on the AP exam. Okay, so we notice something here, and we're going to write it down. We notice that if f is decreasing, okay, then the derivative is negative. Remember, less than 0, those are numbers that are negative, okay? You could even write f prime of x if you wanted to. Okay, now actually let me rewrite this because it works both ways. Okay. So similarly, let's take a look. When f is increasing, what do you guys notice about the derivatives? Okay. Notice that when f is increasing, the derivative is all positive. So f is increasing implies that the derivative is greater than 0, or aka positive. Okay? That's basically this test right here. Okay? So you guys wrote it down. So here's the thing. What separates a function from increasing and decreasing, right? The moment that it stops decreasing and starts increasing, or vice versa, they always encounter a moment where the derivative is 0. They always encounter a moment where the derivative is 0. Back in that last lesson, I want you guys to take a look. There's a special name for that when the derivative is equal to 0. What do we call it, right? Press play whenever you're ready. We call these critical numbers. Okay? So here we go. Here's example 1. We'll do a couple of these just to make sure you guys are comfortable, but go ahead and press play whenever you're ready, all right? Find the open intervals on which f of x equals x cubed minus 3/2 x squared is increasing or decreasing. Okay. So if you want to know if something is increasing or decreasing, the first thing you got to do is to find out where it separates. Okay, remember, a function will stop increasing and start decreasing, or vice versa, the moment where it hits a critical number. So the graph changes directions at the moment where the derivative is 0 at a critical number. So just like the first step to finding the absolute extrema, okay, the first step to finding the direction change, okay, is the same thing. We're going to find the derivative and we're going to set it equal to 0. So here we go. The derivative here is just 3x squared minus 3/2 times 2x. And we're going to set that equal to 0. So our first step is to find critical numbers. Okay. So here we have 3x squared. If I clean that up, that'll be 3x because the 2's reduce out. Okay. Or you can multiply and then divide. Doesn't matter. Right. So from here, I noticed that I need to factor. So I could take out a 3x. What's going to be left is an x minus a 1. So if I use the zero product property here, I find out that x will equal 0 and x will equal 1. If you're not sure how I got that, please don't move on and ask, okay? Okay, so here's what I need you guys to understand. You need to know what everything represents. What did we just find? Right? We found critical numbers, okay? So here's what you guys do. This is probably the big step here. What you're going to do, and you might have seen this in pre-calculus, maybe in integrated math 3, but don't worry if you've never seen it before because it's super easy. What you do is you draw a number line. Okay? We call this a sine chart. Okay? We call this a sine chart. Okay? What you're going to do, okay, and listen very carefully, you're going to draw tick marks based on the amount of critical numbers you have. So here we have 2 critical numbers, so I'm just going to draw 2 tick marks. Not necessarily anywhere. I like to put them evenly spread out, but it doesn't have to be to scale. So here this is 0, and here this is 1. It does not make sense to put 1 and then 0 because you have to go from least to greatest, okay? Okay, I'm going to make a note that this is where the derivative is 0. Okay, And what you're going to do here is this sine chart is for f prime. All right. That way I remind myself of what this represents. Okay. If you can color coordinate, this will really help out. If not, just be very careful about how you mark it. The next step here is we're going to test our values. So we're putting in some test values here in between our intervals. So we have 3 different sections here because we had 2 critical numbers. So if you have more critical numbers, you're going to have more intervals, okay? So what we're going to do is we're going to pick a safe number, a simple number in that interval. So for instance, a safe number over here is 2. Okay, it's clearly after 1. You could pick 10, you could pick 20, you could pick 1,000. It really doesn't matter. But since you're computing, you want to keep the numbers as simple as possible, okay? Okay, the safest number in between 0 and 1 is 0.5 or 1/2. Okay, actually I'll use 1/2 in this case. Sorry, 0.5. Let me scoot that up, that looks weird. Okay, and a safe number to the left of 0 is -1. You could have chosen -10, -1,000. It doesn't matter as long as the number is in the section. It'll work, okay? So what you're going to do here is we have to test it. So if you take a look, I'll highlight it in orange. You're going to use your derivative, but it's always advantageous, okay, to use the derivative where it's super factored. So right here, I want you guys to understand that this is equivalent to this is equivalent to this. So it doesn't matter which one you guys use. They're all equal, okay? But shoot for the factored one, okay? So let me write this in. I'm going to put parentheses around the 3x as well, okay? So to imply that we have 2 factors here. So what I'm going to do is I'm going to draw a little skeleton, okay? Pretty much the bare bones of your factors. So if you guys had 12 factors, you would have 12 different empty factors here. So in this case, we only have 2. So what I'm going to do is I am going to mentally plug in my test values to see what the signs come out to, okay? Now, notice the test values do not have a tick mark, okay? Only critical numbers will have a tick mark because I don't want to confuse it for a test value, all right? So if you can color coordinate, this will be really helpful. If you're only using a pencil or a pen, then definitely don't draw tick marks at your test values, okay? So here we go. I'll test the value 2. Again, we don't care about the number, we care about the sign, okay? So if I plug 2 into here, 3 times 2 is going to be something positive. I don't care that it's a 6, I just care that it's a positive. So I put a little plus sign right there. And if I plug 2 in here, I'm going to end up with something positive as well, okay? So I want you guys to go ahead and plug in 0.5 in the middle interval, and then plug in -1. Go ahead and do that. And then press play when you're ready. So if you did this right, if you plugged in 0.5, you should have gotten positive, then negative. And if you plugged in -1, you should have gotten negative, then negative. Watch out for your signs, you guys, okay? So here's what happens. I know that a negative times a negative will give me a positive, okay? I know that a positive times a negative will give me a negative. And I know that 2 positives obviously gives me a positive, okay? So whenever you have an even amount of negatives, you know it's going to come out positive. If you have an odd amount of negatives, you know it's going to come out negative. Okay, so take a look. We have to make some type of conclusion, okay? And this is where all the money is. Here we go. Let me use green. Okay. Therefore, okay, I know that whenever the derivative is positive, I know that this is where my function is increasing. And I know that whenever my derivative is negative, I know that this is where my function is decreasing. Okay? So here's what we do. Where's my function decreasing? Right? So I take a look at my sine chart. So wherever the derivative is negative, so basically from here to here, I notice that the derivative came out negative right there. So I'm going to say f is decreasing where, right? On from 0 to 1. You're always going to keep it open. You don't want to include the 0 and the 1 because that is where the derivative is 0. Okay? Now, this is where you guys really have to train yourselves, okay? You always have to justify your statement. You're stating that f is decreasing from 0 to 1. How do we know that? Since, or because, right? Since, how do we know that? Since f prime is less than 0. This is where the derivative is negative. Don't say since it's negative. Don't say it's decreasing. Notice how I was very specific. F is decreasing from 0 to 1 since the derivative is negative. Okay, if you want to write f prime as negative, that's fine too. I just think it's a lot simpler to put less than 0. Okay? Okay, so I want you guys to go ahead and write a statement for where f is increasing and justify it. Okay? Go ahead and press play whenever you're ready. So here I know that f is increasing. I'll highlight it in purple here. From the far left to 0, and then from 1 to the far right. Okay, now far left. How far left can you guys go? Okay, far left is negative infinity, you guys. Okay, now remember infinities are always open, so use parentheses. And we get all the way close to 0. Okay, and then it starts back up at 1, and it goes all the way to the far right, aka infinity. Okay, so here's the thing. The reason why you don't draw tick marks on test values is because you might accidentally stop at a test value. Okay, for instance, had I drawn a tick mark right here, I would have accidentally probably stopped at negative 1. But remember, you only stop at a critical number. So that's the reason why we don't do that. All right? Okay, now let's finish this one up. How do we know that f is increasing from negative infinity to 0 and then from 1 to infinity? Since f prime is greater than 0 or f prime is positive. And then that's it. Okay, obviously when we do this for the first time, it takes some time to explain. But you guys will get the hang of it very soon, okay? Okay, so if you have any questions so far, make sure that you pause and you ask me, okay? So take a look. This is our actual picture. We said that the function is decreasing. What color did I use for decreasing? Red, right? Okay, I'll use the same color. So we said that f is decreasing from 0 to 1. And check that out, from 0 to 1, it was decreasing. And f was increasing from negative infinity to 0, which is right there, and from 1 to infinity. So we didn't know exactly how the graph looks like, but with calculus, we were able to figure out the direction of the graphs. So we get a better idea of what it looks like. Okay? Cool. Here's part B. Go ahead and write it down. And try this one out. Go as far as you can. And if you happen to get stuck, press play. Or if you want to verify your answers, you can press play as well. Okay. So we want to find out where the function is increasing or decreasing. First step, we got to find our critical numbers. What's a critical number? A critical number is where the derivative is 0. So here we go. The derivative, f prime of x, should be 12x cubed minus 12x squared minus 24x. And the 5 goes away because it's a constant. I set my derivative equal to 0 because that's what a critical number is, as well as undefined, but we don't have any fractions just yet, okay? Okay, so here I notice that I can factor out a 12x. That's my GCF. If I take that out, I get x squared minus x minus 2. I could probably factor that out some more. That's x minus 2, x plus 1. Okay. And to be honest, you guys, this is where you really reinforce your algebra. So if you're not feeling so comfortable with algebra, you will. Just keep practicing, okay? All right, so with the zero product property, I noticed that x will equal 0 here, x will equal 2 here, and x will equal negative 1 here. I just found 3 critical numbers. Make sure that you guys know exactly what you're doing, okay? So what do we do after we find our critical numbers? We draw a sine chart. Okay, so this is f prime. I'm going to have 3 tick marks because I have 3 critical numbers. I want to put them in order. So negative 1 should appear first, then 0, then 2. This is where the derivative is 0. Okay. Then we throw in some test values. Negative 2, negative 0.5, 1, and 3. The worst thing you guys can do is to pick a value that doesn't belong there because it throws off everything, okay? So make sure that you're picking a number that is clearly in that interval, okay? All right, so here we actually have 3 factors. Notice how I grouped that right there. So I'll draw out the skeleton here. We have 3 factors. And when it's in factored form, it's very easy to find out what the sign comes out to, okay? So you're always shooting to use the most factored form. Okay, so here we go. If I plug in negative 2 into the first one, I should get a negative, then a negative, then a negative. If I plug in negative 0.5, I should get a negative, negative, positive. If I plug in 1, I should get positive, negative, positive. If I plug in 3, I should get positive, positive, positive. Okay? Okay, so 3 negatives here. That's an odd amount, so I know it's going to be negative. Here, even amount, positive. Here, odd amount, so negative. And here, positive. Okay, some of you guys might have picked up a pattern already, and I want to shut that down right away. This happens to alternate, negative, positive, negative, positive. That is not always the case, you guys, okay? It can go negative, positive, positive, positive. It can go whatever it wants to, depending on how the function is, okay? So don't think that, oh, if I figure out the first one, the next one's just going to keep switching. That's just a coincidence here, okay? All right, so your sine chart tells the AP reader nothing, okay? Where you get all your points is where you make your conclusion, okay? So F is increasing. Now, it doesn't matter which one you start out with first. F is going to increase, okay, from negative 1 to 0 and from 2 to the far right, which is infinity. So from negative 1 to 0, union, from 2 to infinity. Now, how do we know that? Since f prime is positive. Okay, you will never get points if you do not justify it. Okay, f is decreasing from the far left to negative 1 and from 0 to 2. If you have a highlighter, this will really help animate that, okay? Since we know that because this is where f prime is less than 0, negative. That's it. Okay, on the AP exam, Putting a sign chart there and leaving it tells the AP reader nothing. You get 0 points, okay? Making that conclusion from your sign chart is where you get all the money, all right? Okay, so here's to confirm that. We notice that f is decreasing from negative infinity to negative 1, so it's going downwards. Okay, but also from 0 to 2. There you go. And there, f is increasing from negative 1 to 0 and from 2 to infinity. So we're able to visualize what that graph looks like just by doing a little bit of calculus here. So again, we found our critical numbers. Okay, we made a sign chart. We tested our values. And then we make a conclusion. For those of you that like steps, okay? We have critical numbers because that's the moment where a function can change directions, okay? And we create a sign chart so that we can see exactly in which intervals the function will increase or decrease. Again, please stay away from vague words like it is increasing, it is decreasing, it is positive, it is negative. Don't use the vague words there. Be very specific, okay? All right, here we go. So we can notice something else here. So here I have two pictures. Okay, and you guys can draw this out as well. Okay, so we know that this right here is where the derivative is equal to 0 because the tangent line is horizontal, so the slope of the tangent line is 0. I noticed that when the graph is decreasing, the derivative is negative, right? And when the function is increasing, the derivative is positive. Okay? That's something that we went over already. Okay, so here's a question for you guys. There was a name for this point in the last lesson. Okay? Think about what that point represented here and here. Right? Press play whenever you're ready. Here on the left, we call that a local minimum because locally it's the lowest point. And over here, this is a local maximum because locally it's the highest point. So what do we notice about local minimums and local maximums? So notice how local minimums transitions from a negative derivative to a positive derivative, or when the function changes from decreasing to increasing. Okay, a local max is where the derivative changes from positive to negative, or similarly when the function is changing from increasing to decreasing. Okay, this right here is our first derivative test. Don't worry so much about the name, just know how to use it. Okay, so here we go. Here's the first derivative test. Before you guys write anything down, okay, just understand it. The first derivative test. When the derivative changes from negative to positive, what I like to do is I like to draw it out. Okay, so if the derivative has a negative value, the slope goes like this. When the derivative changes to positive, it's like this. Okay, notice how we decrease then increase. Okay, so logically that is a local or relative minimum. Write that however you want to write that. Okay, if the derivative changes from positive to negative, okay, we have a local or relative max. Here's how I would write it if you guys want to copy me. Okay, f has a local max. I should write if. Okay, if f has a local max, then f prime changes from positive to negative. If f has a local minimum, then f prime changes from negative to positive. Okay. This is formally called our first derivative test because we're using the first derivative. Okay. But it's very logical as well. If you ever forget, just draw your two favorite curvy functions, the parabola and the upside down parabola. Okay. So again, I try to stay away from remembering rules and just focus on the logic behind things. So if you can understand how things work, you will never have to remember anything in your life, okay? Here we go. So, oh, that third one, I should say. Number 3 here, that's just saying if your derivative is positive to positive or negative to negative, where there's no sign change, then you're not going to have any local extremas, okay? I should include that. You guys should too. If f has no local extrema, then f prime did not change signs. Okay, that was an add-on because, I mean, when you're looking for local extremas, you're either looking for a local max or min, but there is a case where you might not have any, okay? So they show you that graphically here. Here is a local min in the first example where the derivative was negative and then it changed to positive. Okay? Or I should say, yeah, the derivative changed to positive. Here there's a local max or a relative max because the derivative changes from positive to negative. Okay? Notice how when the derivative goes from positive to positive again, there's no local extrema there. I kind of showed that example in the last set of notes with that cubic function. Same thing here, when the derivative goes from negative to negative, there's no sign change. There's no local extrema there either. All right, feel free to draw those down if you guys want to. Okay, so we actually did this problem here, but I'm going to add on to it. Let's call this example 2. You guys can go back up to this same example if you have space, okay? But if not, just call it example 2 and write this out. Find the local minimum and maximum values of the function f. I'm going to go ahead and bring down that sine chart so that we don't have to keep scrolling back and forth. Is it this one? Yeah, I think it's this one. Okay, so here's our sine chart that you got from that example there in part B. So do we have any local extremas? Okay, so remember, we know that there's a local extrema if the derivative changes signs. So did the derivative change signs? Heck yeah, it did, right? In a lot of places. So I know that here and here there is, I should connect these two. The derivative changes from negative to positive, implying that there's a local minimum there. Here, the derivative changes from positive to negative, so there's a local max there. All right? But we have to write it formally. So here we go. Let me erase this. So how do you write it formally? So what has a local max or a min, right? You can't say it has a local max. We want to say f has a local max at x equals. So we know that f is going to have a local max at x equals 0 since f prime changes from positive to negative. I'm running out of space. Okay. Make sure you guys believe it, all right? Since the derivative changes from positive to negative, you know there's going to be a local max there. And we could see in that picture right here. Let me erase this here so you guys can see it. Right there, there is a local max at x equals 0. Okay? All right, so here f has a local min. You could use the word relative if you want at x equals -1, comma 2. Since f prime changes from negative to positive. Okay, it's all in the conclusion, you guys. Take your time with it. Remember, be very specific. Don't use words like it. And that's it. So it kind of builds off of the direction of the graph, okay? So let's do a couple more. Here we go. Oh no, trig functions. Let's call this example 2b. All right. Find the local max and min values of the function g of x, which is x plus 2 sine x, somewhere in between 0 and 2 pi. All right. Now, some things to note. In regards to that last lesson with absolute extremas, some people might see this closed interval and think that it's absolute, okay? But notice how they specifically say local, so you're not going to find absolute there, all right? So pay attention to the little details. Here we go. So if we want to find local extremas, okay, great place to start. Just like where we want to find the direction of the graph, we want to find out where the derivative is 0. So the derivative here, press play when you're ready. The derivative here is 1 plus 2 cosine x. And we set that guy equal to 0 because we're trying to find critical numbers. Now here, you can't really factor anything out, so we can just solve for cosine x. So if we subtract 1 to the other side, to the left side, we're going to have -1 equals 2 cosine x. And if we divide by 2, we're going to get -1/2 equals to cosine x. And this is where you guys got to think about your unit circle, okay? So first things first, where is cosine 1/2, right? You guys always have 3 choices here. It's either pi over 6, pi over 4, and pi over 3. Okay? Feel free to look back if you guys need to. You guys got to be well-versed in the trig ratios, okay? That was the one thing that I wanted from you guys before you jumped into calc. So if you don't know these now, practice it, okay? It's okay, just practice. So cosine comes out to 1/2 at pi over 3, some version of pi over 3. Okay, but notice how this cosine here is negative. So if you remember, all students take calculus, okay? Excuse me. Cosine will always be positive in the first quadrant because it's all in the fourth quadrant. So the only time it's going to come out to -1/2 is in the second and the third quadrant. Okay, if you guys remember the trick, now if you had Miss Tran, she might have shown you that hand finger trick, okay? But there are many different ways. You could probably YouTube different ways to remember it. Here's how I remember it: -1 plus 1 times 2 minus 1. Okay, what I mean by that is, you know that it's going to be some version of pi over 3. Okay, if you're in the second quadrant, you're going to subtract 1 from your denominator. So if you take a look, if there's a 3 in the denominator, 3 minus 1 is 2. You're going to put a 2 here. It's a trick. It's not logical, but when you're dealing with small things like this, you don't want to spend too much time on it. Okay, so if you're in the third quadrant, you want to add 1 to your denominator. That's just going to be pi over 3, but if you take 3 and you add 1, that's going to be 4 pi over 3. Okay, again, you could do the finger trick if you guys want to. Doesn't matter, just know it. All right. Okay, so here we go. If you need a refresher with trig, you gotta reach out to me right now before you move on. Okay. The trig part is just a small part of the bigger problem. So don't judge today's lesson based on this trig stuff. Judge it based on the sign chart, the critical numbers, the testing the values, and the conclusion, right? So this is just a small little hurdle that you guys got to get over if you're having trouble with trig ratios. Okay, let me scoot this over here so we have room. Okay, so we found our critical numbers. We have 2, so we're going to draw our sign chart. This is our derivative, g prime. We're going to draw out the number of tick marks according to how many critical numbers we have. So 2 pi over 3 is going to go first. 4 pi over 3 is going to go next. Okay, and keep in mind that it's capped at 0 to 2 pi right here. So we don't technically go all the way to negative infinity and infinity here, okay? Because with trig ratios, they repeat in values, so they want to make sure that you don't keep repeating yourself, okay? Test values, here we go. Now, assuming you don't have a calculator, you want to pick values that you know that's on the unit circle. So I know that 1 pi over 3 is good here. 3 pi over 3 is good in the middle, otherwise known as pi. But again, that's 3 pi over 3, in case you guys want to see the pattern here. Okay, and over here, I'm going to use 5 pi over 3. All of these orange values I know are on the unit circle, okay? So we're going to have to do a little bit of work here because we couldn't factor it, okay? So here we go. Cosine of pi over 3. So we're actually focusing on this right here. Okay, so we can kind of get away with it, but I'll write it out so you guys see what I'm doing here. In my head, I have 1 plus 2 cosine of pi over 3. I know that pi over 3 is in the first quadrant, and I know it's going to come out positive. And if you multiply with a 2, it's going to be more positive. And if you add a 1 to it, it's going to be more positive. So, in a sense, you don't really have to know what the value comes out to. You just have to know what the overall value sign comes out to. All right? If I plug in pi, okay, I know that cosine of pi is negative 1, so I have to do a little bit of work here. Negative 1 times the 2 is a negative 2, plus a 1 is something negative. Okay? Now, if I plug in 5 pi over 3, okay? Again, 5 pi over 3 is in the fourth quadrant. I know cosine is going to come out positive. So if everything is positive here, I know that the overall value is going to come out positive as well. That's what I mean by you being able to get away with not knowing the overall answer, okay? All right, here we go. So let's answer our question. Specifically, they want us to find the local max and minimum values. Notice here they didn't really ask us where is it increasing or decreasing, okay? So pay attention to the phrasing of the question. All right, here we go. So we know, therefore, G has a local max. Do we have a local max here? We do. At x equals 2 pi over 3. Since G prime changes from positive to negative. Okay, right there. Okay, go ahead and write your other statement now and press play when you're ready. G also has a local min at x equals 4 pi over 3. Since G prime changes from negative to positive. Obviously, I have no space, but you guys do, okay? That's it. All right. Let's do let's do this one. Okay, call this example 5. I don't know my numbers. Okay, write it down. Find the relative extrema. Okay, so they're asking us for local extremas. So what do? We find the derivative. Okay. But I noticed that there is a function inside of another function. You guys got to know your rules very well. So this is going to require the chain rule. Go ahead and implement the chain rule there. Press play whenever you're ready. So here it's the derivative of the outside. So 2/3 of something to the negative 1/3. Derivative of the outside of the same inside times derivative of the inside, which is 2x. I'm going to set this guy. Actually, you know what? I'm not going to do that just yet. F prime of x will now equal, I know that x squared minus 4 to the negative 1/3 is going to go down below because it has a negative exponent. So the only thing that stays on top is the 2 and the 2x, which makes 4x. Down below, I have a 3 and x squared minus 4 all to the 1/3 power. Make sure that you guys understood what just happened there. So the reason why I'm showing you guys this problem is because a lot of people tend to forget that a critical number is either when the derivative is 0 or undefined, okay? So when you have a fraction, it's possible to have both. So think about this logically. If you have a fraction and you wanted to make it go to 0, do you set the top or the bottom equal to 0, right? If you want the whole thing to go to 0, you set your numerator equal to 0. If you want the whole derivative to be undefined, you set your denominator equal to 0. Okay? So here we go. X is going to equal 0 here. And if you solve this far enough, you should get x equals plus or minus 2 because you end up square rooting, okay? If you're not sure how I got that, let me know. Okay, so here's checking for understanding. What do those represent there, right? Okay, those represent the critical numbers. So we have 3 critical numbers here. We have the 0, the plus 2, and the minus 2. After we find our critical numbers, we create a Sine chart. So here we go. This is for the derivative, okay? We have 3 different critical numbers. So negative 2 should go first, then 0, then a positive 2, okay? At 0, this is where the derivative was 0. And at plus or minus 2, this is where the derivative is undefined. Okay. All right. Test values. Negative 3, negative 1, 1, and 3. All right. Now, the most factored form is this right here. So I'm going to go ahead and group that. Group that. So we have 1 factor at the top. We have 2 at the bottom. Now, I noticed that 3 is constant. So 3 will always be positive no matter what. So I'm going to put a little positive in there. Okay. So let's focus on just the numerator. If I plug in negative 3, I get something negative. Negative 1 will give me something negative. 1 will give me something positive. 3 will give me something positive. Okay. if I plug in, let's start off on the right side here. If I plug in 3 into x squared minus 4, so 3 squared will give me 9, minus 4 is 5. If you cube root it, you get something positive. Okay? If you plug in 1 squared is 1, minus 4 is negative 3. If you cube root it, you end up with something negative. It's different from a square root, you guys. Okay, if you plug in negative 1 squared, you still get a positive 1. Minus the 4 is a negative 3. Cube root it is something negative. And if you plug in the negative 3, same thing, you get positive 9 minus the 4 is a positive 5. Cube root it, you get something positive. Okay, you count the number of negatives. Here, we're going to end up with an odd number of negatives, so we have a negative here. Even number of negatives, we have a positive here. Negative, positive. They happen to alternate. But again, you guys, they don't always alternate, all right? Find the relative extrema. Okay, so go ahead and make your conclusions, okay? Press play when you're ready. Therefore, f has a local max at x equals. So let's see, a local max would be at x equals 0, since f prime changes from positive to negative. F has a local minimum at x equals negative 2. And what am I missing? And positive 2, since f prime changes from negative to positive. But let's see, okay? Let's take a look at the picture to see if it's accurate. Okay, we had a local max at x equals 0, local min at negative 2 and plus 2. That looks good, okay? So if you guys notice, if we forgot that a critical number is where the derivative is 0 or undefined, if we forget the undefined part, we would have missed out on these two right here. The reason why the derivative is undefined there is because notice how it's like a sharp corner. You can't draw a tangent line there, a unique tangent line. So make sure that you guys remember that a critical number is where the derivative is 0 or undefined when you're dealing with fractions, okay? Because if you forget it, you're going to omit a lot of it, all right? Okay, here's the last part. Particle motion, okay? So let me give you guys a quick introduction to it. Particle motion is an application, okay? You're dealing with distance, you're dealing with velocity and acceleration, okay? So I believe I talked about it before, but if I didn't, it's okay. I think I did. S of t represents like your distance. Actually, no, I should say your position. It's where you are, okay? Now, if you take the derivative of position, s prime of t, that actually represents the velocity, how fast you're going, okay? This is your velocity. Now, if you take the derivative one more time of s, or if you take the first derivative of v, you're finding out how fast your speed is changing. And if you think about a car, how do you change the speed of your car? You have to accelerate. So this is acceleration. If you've taken physics or are taking physics currently, you will notice these three. Don't worry if you're not. But here we go. So all you have to remember is SVA. That's the order, SVA. One of my previous students made an acronym called salted very almonds. It makes no sense, but it was so dumb that I remembered it too. Okay? Feel free to make your own acronym to the point where it sticks, but SVA. All right? Okay, so here we go. So let's say that you have this particle. A particle is just an object, okay? And this particle is moving in either two directions. It's either moving left and right, or it's moving up and down. Okay, but not both. Okay, so for the sake of argument, let's just say that you have this object that can either move right or left, okay? And they give us the position function here. Describe the time intervals when the particle is moving to the right, moving to the left, and what particular time the particle is changing directions. Okay? So here's what's happening, you guys. You have this particle, okay? We want to know where the particle is moving to the right. So think about it. If you're on a number line and you're moving towards the right, are you increasing in value or are you decreasing in values? Okay? If you think about a number line, if you walk towards the right, the numbers are getting larger, meaning that you're increasing in value. Okay? If you're moving to the left, you're really decreasing in value. So it's the same thing here, you guys, but with a little application. So what we do is we find the derivative, which is v of t, aka s prime of t. The derivative of s of t is just going to be 14 minus 2t. We set that guy equal to 0 because we're finding what first, right? We're finding out our critical numbers. Now you could factor it here. You'll get 7 minus t. You find out that t equals 7, okay? Okay, what is that? That is our critical number. So here we go. 7. I put in a test value. 1. 8. Okay, doesn't matter what you pick, but remember t is time, you guys. Don't pick negative 1 million because time cannot be negative, all right? Now, here, my bare bones is a 2 times something, 2 times something. So I know that first one, it has to be positive because it's a constant. But if I plug in 1, 7 minus 1 is something positive, and 7 minus 8 is something negative. So here I end up with something positive, and then here I end up with something negative. So here we go. Therefore, okay, the particle is moving to the right. Remember, when the particle is moving to the right, that implies that the particle is increasing, okay? So where is this increasing, right? Wherever the derivative is positive. So pretty much right here. From where to where? Okay? So remember, you don't want to say negative infinity to 7 because t is time. So you want to say from 0 to 7. From 0 to 7, since, and you could use either of two things. You could say since v of t is positive, or you could even say since s prime of t is positive. It's up to you, okay? Okay. Now the particle is moving to the left. I'm running out of space, so I'm shorthanding this, but you guys should write out the whole thing. The particle is moving to the left from 7 to infinity, since v of t or s prime of t is negative. Okay? Does the particle change direction? So the particle started moving towards the right, and then it decides to turn around and move left. Okay? So we know that there's a change in direction. Okay? So the particle changes directions at t equals 7, okay, since v of t changes signs. Okay, now because of the phrasing of this question, you guys, okay, it doesn't change directions because the derivative changes from positive to negative, all right? Because even if it's from negative to positive, you know that this particle or this worm or whatever you want to think about is changing direction. So here we can say that it just changes signs because there's context, okay? I'm going to have you guys try that. I think I have one more for you guys. And then we're all done, okay? Let's try this one out. Write it down. Here's S of t. Now, instead of moving left and right, this particle is moving up and down, okay? Try this one out and then press play whenever you're stuck or ready, okay? So we want to know where the particle is moving up, down. So AKA moving up means increasing. Moving down means decreasing. And wherever it's changing directions, pretty much wherever there's a local extrema, okay? Here we go. So first step, find your critical numbers, which is where the derivative is equal to 0. You should get 2t squared minus 7t plus 3. You set that equal to 0. You could actually factor this. 2t minus 3 minus 1. T comes out to 1/2. T comes out to 3. Okay, those are my critical numbers. So here we go. This is going to be S prime. I have 1/2. I have 3. You could even put a blocker at 0 to remind yourself that time has to stop at 0 or start at 0. Test values, okay, 1, 4. This first one here might be hazy, but if 1/2 is 0.5, you could do 1/4 or 0.25. It doesn't matter. As long as you're in that interval, okay? So we have two factors here. Right? If I plug in 4, I'm going to get positive, positive. If I plug in 1, I'm going to get positive, negative. If I plug in 0.25, I'm going to get negative, negative. Okay? So that gives me a positive, that gives me a negative, that gives me a positive. They happen to alternate. Okay? All right, so where's the particle moving up? The particle is moving up or increasing when the derivative is positive. So the particle is moving up from 0 to 1/2 union 3 to infinity. If you guys take a look, this is where the derivative is positive. So since v of t or s prime of t is greater than 0, okay, the particle is moving down or decreasing in value from 1/2 to 3 since v of t is less than 0 or s prime of t. So I'm using both to show you guys the flexibility there, but you don't have to have one of each, okay? So does this particle ever change directions? Yes. The particle changes directions 2 times. Okay, at t equals 1/2 and at 3, since v of t changes signs. You guys got to understand that changing directions here imply local extremas in general, not necessarily a max or a min. So here we can say just changes signs, okay? Because there's context. Okay, so to wrap this up, you guys, we found out how f is increasing and decreasing, and we know where the local extremas are. First, we find our critical numbers. Okay, set it to 0. Actually, no, critical numbers is where the derivative is 0, so that's kind of redundant. Okay, 2, sine chart. Okay, 3, test your values. 4, conclude. Okay. That's it, you guys.